period of several decades were not maintained as well as they should have been. And by the time the public and the technical experts became aware of this, sometime during the mid and late 1970s, large amounts of damage to structures was accumulated already. They had deteriorated beyond the point where they could be just maintained.
Cities which grow in prosperous times may turn out to be a costly inheritance for those who follow. Less visible than roads and bridges, but just as important to a city's life are its sewers. The construction of Tokyo's sewage system began early in the 20th century. In the first 30 years, about 2,000 kilometers of sewers were constructed, mainly under downtown Tokyo. Then, reflecting the explosive rate of Japan's economic growth, Tokyo's development took off, and the growth of its sewage system had to keep pace. The sewers in the district around Ueno Station are among the oldest in Tokyo. Today, the total length of the drains under Tokyo is about 14,000 kilometers. Robot cameras such as this examine the system's branch pipes. The camera discovers cracked joints. And tree roots which invade the system. Nearly 2,000 kilometers of branch pipes have been in use for more than half a century and desperately need maintenance. In the summer of 1993, Typhoon number 11 wreaked havoc, dropping 65 millimeters of rain on Tokyo in 1 hour. The sewage system was badly damaged. At one place in the Taito district, sewer pipes were broken and roads caved in at 13 points in a 170-meter stretch. It was the breaking of the sewer pipes that undermined the road. The city of Tokyo has developed a unique technology for repairing smaller pipes. It's a form of construction by remote control. A flat vinyl chloride strip is spiraled into the old pipe, creating a lining which in effect is a new pipe slightly smaller than the old one. The advantage of this method is that the functioning of the sewer can continue without interruption. The maintenance of urban infrastructures is made doubly difficult by the disruption which inevitably follows when facilities have to be closed for repairs. Nine kilometers of Tokyo Highway number 1 has been shut down completely for intensive repairs. This is one of Tokyo's oldest roads. Normally, it serves an average of 80,000 vehicles a day. For one whole week, 80,000 vehicles will have to find a different route. The total volume of traffic on Tokyo roads is 1.15 million cars and trucks a day. New roads are being built while the need for maintenance is escalating. The maintenance department keeps a pictorial history of roadbed conditions. It now consists of almost 300,000 pictures. This is a special road inspection vehicle. The department calls it a techno-checker. The techno-checker uses laser light to inspect roadbeds. The laser beam can detect cracks as small as 1/5 of a millimeter wide. The roadbed is the heart of a highway. If cracks are not attended to, the road disintegrates. This machine is rolling a 15-ton load on a test sample of highway concrete, a load equivalent to a fully laden truck. In its 5th day of testing, the loaded wheel has passed back and forth more than 200,000 times. The deflection of the test sample is slowly increasing. Cracks are appearing all over. The condition of the sample is equivalent to the condition of an actual highway after 15 to 20 years of use. Complete closure of Highway 1 is essential to rebuild the roadbed. More than 100 kilometers of Tokyo's roads need this kind of drastic maintenance. Temporarily closing parts of a city's infrastructure from time to time is unavoidable. In 1993, an unusual public school was established with 130 New York students, as well as regular curriculum. Students study infrastructure. School founder Samuel Schwartz used to be responsible for city bridges.
The wire was then longer. It all stretched out and it's elastic. The roadway actually drops. And one day what we did, and it wasn't just for fun, we took all the people off the bridge, but we loaded it up with trains from end to end. So every inch was filled with trains on the tracks.
On one field trip, Samuel Schwartz took his class to visit the Williamsburg Bridge, which is under repair. Schwartz believes that engineers of the future must be trained to fix as well as build.
So how old are you now?
12.
12. When you're 22, the bridge should be finished. And when most of you, I guess, are in your 20s, the bridge will be finished. You know what that means? It's going to be your job to make sure that we never make this mistake again. So you could dream then. We could have a city in which you could have lots of dreams and you can make those dreams happen if we all do the job right. So we're starting with you guys. Some of us have already made mistakes, but you guys will pass this all on.
A city's well-being depends on maintaining its infrastructure. The task is daunting, but history gives us hope. In the mid-19th century, Napoleon III ordered his prefect, Georges Haussmann, to rebuild Paris, replacing old, unhealthy, winding streets and adding central sewers. Haussmann gave the burgeoning city major new infrastructure. Paris is still growing and changing, giving life to a new sub-city, La Défense, a gift of infrastructure from our generation to the future. We live in the century of civil engineering. We must continue to build public infrastructure which will not only keep us in health and safety, but will be our lasting gift to those who follow us in the next century. Iguazu Falls, the largest in the world, between Brazil and Argentina. Translated from the local tongue, Iguazu means mighty water, and this indeed it is, a thundering cascade 5 kilometers wide. Upstream nearby on the Parana River is another falls, another mighty water, this one controlled by the Itaipu Dam, a marvel of 20th century civil engineering, a reordering of nature to serve the needs of man. Winning power from nature has been a key to the history of human development. This is no contest. Such works are only possible if nature is approached with imagination and respect, and the clear understanding that nothing is accomplished without her permission. A streetcar and an aqueduct, the city of Rome, where the past is ever present. Imagine Rome in the 1st century, the hub of the Western world, a gigantic city in its time of 400,000 souls. Where did ancient Rome get its water? There was drinking water in the streets. There was water for washing and for cooking. And water for the fountains and the gardens. There was water for the sewers. And water for the public baths. The supply per person is said to have been larger than that supplied in modern Rome. Among the most important public works of ancient Rome were aqueducts, the raised canals which brought the water used for drinking and bathing, gardening and sanitation from hills many kilometers distant. Mybudo, Iran. In this desert climate, the water would quickly evaporate from aqueducts. Tunnel technology was developed to bring water to places where the local source was insufficient. These tunnels, qanats they are called, have been built in Iran since 800 BC. People who excavate the qanats are called mogani. As a first step, mogani dig a vertical hole to the required depth for that point in the system.
حالا هر چقدر موقع میکشی بره. میگی چه؟
This qanat is 30 meters deep.
داری؟ میگم نه. اوی!
The tunnels are just wide enough for one person to get through.
شما نمیتونید بید بگن نه. من رفتنش میرم.
There is no framework of any kind reinforcing the tunnel, except at the entrance.
ببینید این توی دهنه کبر 60 سانت.
In 2,800 years, the Mogani have learned how to use the soil itself to prevent tunnels from collapsing.
این الان میبینید این.
The Mogani are specialized civil engineers. The engineering mentality has made it possible for human life to thrive in some rather unlikely environments. The 1869 Suez Canal is a channel of a different order, one which brought Europe and Asia closer together. This great ditch in the desert significantly altered the infrastructure of world trade. Shortly thereafter, early in the 20th century, another major trade route came into being with the opening of the Panama Canal. These mammoth engineering achievements were landmarks in the globalization of human affairs. The Dutch have been winning land from the sea for 700 years. This is Flevoland in Holland. It was once the sea. The Zuiderzee was shallow, 5 to 10 meters deep, but indisputably sea. Huge areas were cut off and contained by dikes, and the seawater was pumped out. 1/4 of Holland is now reclaimed land. Drainage of the newly acquired land had to be the first priority. As it dries, the land will subside. Buildings are supported on concrete pilings driven through the soft clay of the former seabed to a firmer layer below. The Dutch say, God made the world, but the Dutch made Holland. The heart of the reclamation enterprise is the pumping station. The land it serves is 5 meters below sea level. The drainage system returns water via the pumps to the sea. The 20th century has made enormous strides in the technology of water control. 29 billion tons of water are held back by the Itaipu Dam on the Parana River in South America. It's a joint project by Brazil and Paraguay, 7 kilometers long and over 200 meters high. This one dam generates 12 million kilowatts, enough to supply a third of Brazil's requirements and more than Paraguay can handle. It's one of the largest in the world, 33 million tons of concrete, equivalent to the volume used in all the buildings in Rio de Janeiro, a sobering indication of the pressure the dam is required to withstand. An elevator takes the inspection crew 140 meters down to the bottom of the dam. A crew keeps watch 24 hours a day. It is down here at the foot of the dam that vital signs are monitored. Water has squeezed through the 200 meters thickness of the wall, an indication of the enormous pressure from the reservoir behind. No leak can be ignored, but some seepage is expected. Stress will cause distortions in the body of the dam. This device reads data provided by 3,000 strain gauges. White bars embedded in the concrete respond to stress by expanding and contracting. The positioning of the bars makes it possible to analyze the direction of the strain. The most important indicator of the dam's overall condition is a simple plumb line. It's a weight suspended on a wire 140 meters long, which is attached to the top of the dam. An apparent shift of the plumb bob at the bottom of the wire indicates that the top of the dam has moved, bending before the force of pent-up water. It's a simple instrument, but it does a very important job. The Itaipu Dam, one of the great dams of the world. With a work of this magnitude, care can never be relaxed. History shows that nature does not forgive our trespasses. June 1976, Idaho, USA. The Teton Dam suddenly collapses.
At 11:57 a.m. on June 5, 1976, the Teton Dam collapsed, flooding homes and farms in the upper Snake River Valley with 80 million gallons of water.
The Teton Dam was intended to provide water for agricultural irrigation. Instead, it took several lives and washed away 1 million dreams. The accident was caused by a tiny leak, which was rapidly expanded by the enormous pressure of the water behind, and the river broke free. The site of the collapse remains as nature left it. The Teton Dam is not the only one that failed. Modern dam technology owes a lot to failures. It's partly due to these grim lessons that during the 20th century, dams have been enabled to grow tall, from 70 to 300 meters high. This is the Urayama Dam, under construction in Japan. One of the big problems that dam engineers have to face is the nature of the rock below and around the dam. The dam itself is one component in a system. Behind it will be a lake that nature never intended. The lake will exert tremendous pressure on the bedrock below and around the dam. So what is the character of the local rock? A tunnel was dug to investigate.
"石になった時代が2億年ぐらいとか古い時代のものですから、こういったところにずっと。
The rock is a maze of fractures, unlike the monolithic concrete mass of the dam itself.
石と思われがちですけれども、いろいろな種類のものが積み重なったり、あるいは風化したりしておりますので、こういったところに空間があるとか、あるいは粘土が入ってきて詰まっている状態のものが水道になるわけです。
If water seeps through, around the ends, or underneath the dam, it could lead to collapse. Seepage must be stopped. But how? The Miyagasi Dam in Kanagawa Prefecture will be Japan's largest concrete dam, providing water for over 1 million households. It's 400 meters wide and 155 meters high. The reservoir will hold 200,000 tons of water. What is the nature of the bedrock here? Will it be impervious to seepage under pressure? Instead of a tunnel, a hole has been drilled and a special camera will be used to examine the geology. The bedrock begins 5 meters down. This is 8 meters down, well into the bedrock. The rock here appears to be just as fragmented as the rock at Urayama Dam. Here is a graphic representation of the threat posed by fractured bedrock. Water infiltrates the cracks in the rock underneath the dam. This water thrusts against the bottom of the dam, empowered by the enormous pressure at the bottom of the reservoir. The upward thrust combined with the push from behind is a recipe for disaster. The higher the dam, the deeper the reservoir, and the greater the pressure at the bottom, ready to destabilize the dam if the water can get underneath. The solution is to seal the bedrock. A tunnel is bored into the bank beside the dam. A series of deep holes is drilled down into the bedrock from the floor of the tunnel. A mixture of cement and water is forced into the holes under pressure. This cement milk is forced into all the cracks that the hole intercepts. The holes are close together, so the result is a sort of curtain within the bedrock through which no water can pass. Once again, a camera is lowered into the drill hole. Green, shimmering areas show where cement milk has hardened, even in tiny cracks, 110 meters underground. At the Miyagasi Dam, the curtain of grout stretches across an area 3 times as wide as the dam. The method is called curtain grouting. It was developed in the United States and is now standard procedure for modern dam construction. The more we demand of nature, the more problems we uncover. But as we solve the problems, we discover new technologies. The Miyagasi Dam is the largest mass of concrete in Japan. Concrete heats up as it hardens. The cable this man is burying is like a nerve. It contains an optical fiber, the kind used in communication systems. Heat sensors take the temperature of the concrete at various points within the dam. The 4 kilometers of cable buried in the dam bring this information to a control room for analysis. The control room is inside the dam, 150 meters from the top. This chart shows how the cable winds around inside the dam. The vertical axis shows the temperature, and the horizontal axis shows where that reading comes from, its distance from this location. The center of the dam is much hotter than the outer region. All concrete gets hot as it hardens because of the chemical reaction of cement with water. But heat generated in the middle of a dam is trapped, so the temperature rises. Why should this concern us? A simulation was prepared by the Ministry of Construction's Institute of Public Works. Concrete heats up as it hardens. When the reaction is complete, it cools, and as it cools, it shrinks. But the parts which are fixed to the bedrock cannot move, so the dam warps and cracks. Heat, therefore, is a problem. This experiment shows the relationship between cement content and heat generation. These 2 samples have different compositions. Standard concrete on the left contains 3 times as much cement as the one on the right. The one with more cement generated a temperature 20 degrees Celsius higher. Until recently, attempts to solve the heat problem in dam construction focused mainly on how to cool the concrete after it was laid. The builders of the Miyagasi Dam took a different approach. They are using concrete with very low cement content to reduce heat generated in the first place. It's called roller compacted dam concrete, RCD. RCD was developed for dam building in Japan by improving American roller compacted concrete. It generates 20% less heat than traditional mixes, and this is attracting worldwide attention as a means for dealing with the heat problem in dam construction. A number of procedures are used with RCD to keep the temperature of the concrete down. To protect ingredients for the concrete from the heat of summer, a refrigerating facility was constructed next to the plant where the concrete is manufactured. Large volumes of air chilled to less than 10 degrees Celsius are fed into the plant to cool the materials. Temperatures are closely watched. Cold water is used in the manufacture of the concrete. Even in the heat of summer, its temperature is kept below 10 degrees Celsius. The mixed concrete is sent to the construction site at once before its temperature can rise. Steel plates are inserted in the concrete before it sets. These act as buffers. They absorb stress and reduce the likelihood of cracking. Because of its low water content, RCD concrete is relatively dry. A special vibrating roller is needed to compact it. Engineers have responded to society's insatiable demands for power and water by building bigger dams and finding new technologies along the way. These great works and the forces of nature they confront are rarely ever seen by those who most benefit from their existence. A new airport for Hong Kong, the largest one in Asia, scheduled for completion in 1997, the year Hong Kong reverts to China. The site for this mammoth project must be constructed by filling in the ocean as well as leveling the land. Tokyo's Haneda Airport is also expanding. The new terminal was built on land reclaimed from Tokyo Bay. New Kansai Airport in the Bay of Osaka, the world's first offshore airport, is built on an artificial island in the sea, 5 kilometers offshore. Airports that encroach on the sea are becoming popular in Asia, and new technologies for land reclamation are evolving. The Dutch take land from the sea by driving it back and building walls to keep it out. In Osaka Bay, the seabed was built up into an island that is the site of Japan's newest and most splendid airport. But what is the nature of the land on which this airport sits, and what technologies were involved in its creation? Eight towers have been posted in the sea around New Kansai Airport Island. Every month, the level of the island is checked from these towers to find out how fast the island is sinking. In the past 6 years, it has dropped 10 meters. It is now sinking at the rate of about 1 millimeter a day, and evidence of the sinking can be seen in this well, which goes down 200 meters below the ocean floor. The island's weight is squeezing water out of a 1-million-year-old water table 200 meters below. As long as the island sinks, the water will keep flowing. Why does the island sink? New Kansai Island sits on a layer of clay 20 meters thick. 70% of the volume of the clay is water. The weight of the island slowly squeezes water out of the clay. Its volume is reduced, and the island sinks. They say that left to itself, the sinking could go on for as long as 100 years. It can't be stopped, so the best thing to do is to hasten it to achieve stability as soon as possible. To do this, we must accelerate the draining of the clay. 10 of these ships are key to that technology. Each ship is equipped with an array of steel tubes, 50 meters long and 40 centimeters in diameter. These pipes are driven down into the soft clay. Clay in the tube is removed and entirely replaced with sand. The whole operation, drilling, coring, and filling with sand, is controlled from here. When the sand is in place, the tubes are withdrawn, leaving columns of sand standing in the clay. Here's the sequence. The sand drainer moves into position. The brown layer is the clay. The tubes are down, the clay removed, and they're filled with sand. Finally, tubes are withdrawn, and 6 more sand drains are in place. With the seabed pressed by the weight of the island, water in the clay will escape by draining up through the more permeable sand. As water escapes through sand drains, the clay's volume shrinks and the island settles. A million of these drains were put in place, and the island was delivered, barge load after barge load. $178 million cubic meters of soil went into the making of new Kansai Airport Island. Sand drain technology has shortened the period of sinking from 100 years to 2. Haneda Airport, Tokyo. The new air terminal was opened in 1993. They are now preparing the base of a new runway. The site was formerly a dumping ground for sludge dredged from the bottom of Tokyo Bay. The ground is even softer and wetter than that below New Kansai. Land-based sand drainers were brought to the rescue. Sand drains only work if the continuity of the sand in the column is unbroken. In soggy ground like this, the sand columns are prone to sag and diffuse. Reinforcing mesh made of synthetic resin was introduced to help the sand conduit keep its integrity. The column may bend and twist, but the mesh will keep the sand together so it can do its job. In some locations at Haneda, another dewatering technique was used called paper draining. Long strips of synthetic fiber were thrust deep into the sludge. Paper drains were developed in Sweden, and the material originally used was in fact a kind of paper. The water rises by capillary action in grooves on the surface of the strip. The strips can be inserted very close together. This is another example of a technology which tries to accelerate rather than obstruct a natural process. Kobe Port Island, the modern world's first attempt to build a city in the ocean. Construction of the island began in 1966. An anticipated rate of sinking was built into the schedule. But while reclamation work was still in progress, it became apparent that the island was sinking faster than expected. And now, nearly 20 years later, the sinking continues, and the city is plagued by problems. This monorail roadbed was originally flat. Three steps were added here to adjust for sinking. Nothing fits. Buildings in the land they sit on have different agendas. The problem was the seabed. The soft clay layer was squeezing down according to plan, but the layer below, which was thought to be relatively firm, was sinking faster than anyone expected. This sent a warning to the planners of the proposed new Kansai airport, where the structure of the seabed was similar. The artificial island is green. The soft clay layer with its sand drains, yellow, just 20 meters thick. Below that is the deep layer of supposedly firmer diluvial clay, which was now under suspicion. How would it respond to the weight of the artificial island? In 1981, intensive seabed drilling was done at the new Kansai site. Drillers found a solid floor, but the firmness of diluvial clay atop that floor turned out to be very varied and generally softer than expected. This made it difficult to predict the rate of sinking, but a decision had to be made, and the island was built. This great sinking island is the uncertain base for 200 sinking buildings, buildings of assorted sizes, sinking at different rates, and with parts that sink at different rates from other parts. The response of the engineers to this scenario is a schedule of adjustment. The terminal building is the largest, 1,700 meters long. 900 columns in this building, all equipped with hydraulic jacks, make the building vertically mobile. For lifting purposes, the building is divided into blocks, each with a set of jacks which can be raised in unison. Each column bears 400 tons of building and has 2 jacks, one on either side. The differential settlement of New Kansai Airport came as no surprise. After all, different parts of the island were filled at different times. The white line indicates the site of the terminal building. The animation shows the reclamation sequence. The maximum difference between reclamation times was 7 months. The different blocks into which the new Kansai terminal building has been divided to allow for differential settlement and sequential lifting are connected by flexible rubber joints. These joints at intervals of 150 meters let blocks move independently. Ceilings sit on the columns, and the walls and every other feature of the building hang from the ceilings. Most stairways we encounter sit firmly on the ground, but this one is suspended from above. Ducts and conduits which run the length of the building must be flexible as well, including, of course, the air conditioning system. Walls and stairs and services are in position, and the section is ready to be lifted. There are 2 jacks on every column. The raising of all 10 columns is coordinated here. Hydraulic pumps have started, raising the columns between 28 and 38 millimeters. Failure of any one of the 20 jacks could result in warping or tearing of the structure. Everyone watches and listens. No creak or bump can be ignored. It took 9 days to adjust 73 columns. This type of operation will go on for 30 years. Still all in one piece. Steel shims are put in place to fill the gaps left by the rising columns. Nearly there. 1 to go. That's it. The section is intact. The final shim for this episode of raising has been tapped in place. The hydraulic jacks can rest. Until next time. The Kansai project takes account of the need to jack up buildings for 3 decades. When dealing with nature, the essential key is balance, never confrontation. Venice, the city of 100 islands, has been sinking for 1,000 years. The prosperity of Venice grew on the rich trade of the Mediterranean and Adriatic seas. No city was ever so dependent on the sea, and its roots are in the sea. Its brick and stone stand on wooden pilings driven deep into waterlogged ground. Venice was built on tidal flats like these, not far away. It began as a scattering of huts 14 centuries ago, when buildings were small and few. Wooden pilings simply reinforced the shoreline. Then in the 10th century, and for centuries thereafter, wooden pilings were used as foundations for structures of brick and stone. Deep in wet ground, wooden pilings do not rot. They are as enduring as the stones above them. The greater the weight of the building, the greater the number of pilings needed for support. In the foundation of a tower, they were packed shoulder to shoulder. Venice grew up on wooden roots and flourished, but its history has been one of constant adjustment to sinking and flooding. Some excavating has been done at San Lorenzo's church in southwest Venice. This church was built in the 12th century. A meter below its floor, archaeologists discovered the floor of another building, which was standing on this site 100 years before in the 11th century. Digging continued. Still further down, well underwater, a third floor was found. This one belonged to a 9th century building. It sat directly on the ancient wooden pilings. The foundations of Venice are forever being reclaimed by the sea. Sea level has special meaning for Venetians. The Venetians used to boast that their city was the mistress of the sea. That may well be, but every now and then the tides rise just a little higher to remind them who is master. September 1992, a celebration. Two great seas have been linked by a great canal. The Rhine-Main-Donau Canal completes a 3,500-kilometer waterway linking the North Sea with the Black. Canals have been a part of transportation infrastructure for a long time. Many canals in service today were developed in the 19th century. In Britain, most are even older. Locks are a long-established way of carrying ships between the levels in a system. Vessels sometimes hitch rides on special railways that haul them up slopes in giant tubs, in this case over 1,400 meters. Some systems lift ships in elevators. Design of the Rhine-Main-Donau Canal was inspired by the belief that nature and economic man can live in harmony together. Artificial channels had to be dug at certain points to create the transportation route and allow for water resource, hydropower, and flood control management. Many technologies united to ensure that other ends were served as well: recreational, aesthetic, and ecological. Wherever possible, the canal route followed the river's natural course. Pools and lagoons were deliberately cut to sustain wildlife. This is called close-to-nature engineering. Natural vegetation discourages erosion and moderates water flows in times of flood. Secondary channels released from restraints were restored to their natural meanders. Stones are used instead of concrete blocks to tame the flow of running water. Mesh will help grass take root, guarding the bank against erosion and generating a host of life forms. The Aachen University of Technology has been developing close-to-nature river engineering for 20 years. Here, civil engineering and the natural sciences work hand in hand. It's a new and exciting challenge for all concerned. Simulations like this show how trees planted on riverbanks will alter river flow. Simultaneous research into the ecology of natural systems will eventually result in a brand new, all-embracing technology, linking human endeavors and nature's own works. In the past, civil engineering has confronted many natural obstacles, attempting to conquer them in its attempts to better human life. Learning from failures, civil engineering is striving for new technologies, which will allow it to build new infrastructures on a major scale. And yet, we are looking beyond old ways of doing things. Attempts to overwhelm nature are giving way to methods by which engineers can work with nature in harmony.